Okay. Okie dokie. So our first speaker is Professor Thomas Szkopek with the keynote talk Mechanical Computing Redux. So we will start with a short bio introducing Prof. Szkopek. So Prof. Thomas Szkopek is a professor in the Department of Electrical and Computer Engineering at McGill University, an associate member of the Department of Physics, and a member of the McGill Center for the Physics of Materials. His research interests are focused on the fundamental science and application of 2D materials, including graphene, hydrogenated graphene, graphene oxide, black phosphorus, and stannous selenide. He made important theoretical contributions on the study of charge transport and these two-dimensional materials. On the application side, his work with graphene oxide has led to the commercialization of graphene oxide acoustic transducers for consumer electronics and other applications such as graphene-based pH sensors and microwave devices. These have resulted in the formation of several startup companies in the Montreal area. Prof. Szkopek has received several prestigious awards such as the Canada Research Chair in Nanoscale Electronics, the Hydro-Québec Nano Engineering Scholar Award, and the Carrie M. Derrick Award for graduate education for exceptional mentorship of graduate students. Professor Szkopek completed his PhD with Prof. Eli Jablonovich at the University of California at Los Angeles, UCLA in 2006, and received a Bachelor of Applied Science in Engineering Physics and a Master of Applied Science in Electrical Engineering from the University of Toronto in 1999 and 2001, respectively. So without further ado, Prof. Szkopek.
Right. Thank you, Kens, for the overly kind introduction and perhaps overly detailed. Now everyone knows just how old I am. So I presume everyone can see my slides? Well, I will presume so. So I'm going to tell you a brief story about one project in our group, and it has to do with mechanical computing. So the start of this story is by thinking about energy usage in computing. And here is a recent graphic that shows projections for where we are. Well, it's not a projection if we talk about where we are now, but if you go to years beyond 2020, let's say up to 2030, and we look at energy consumption related to wireless and wired networks, the production of ICT materials, and consumer devices and data centers, we see that actually data centers are gobbling up more and more energy. Forecasts are something like 20% or 21% of all global electricity production being consumed by computing. And in some ways, this is a statement about the success of electronics. It has become so omnipresent, and we are becoming more and more reliant on it that it is no longer a negligible factor for energy usage. And in fact, the story is even more alarming in some ways. So here's a photograph of a Google data center, and all these pipes are being used to carry water to and from the heat exchangers in the data center, essentially carrying away the waste heat from the data center. Something like 40% of all the energy in a data center is just energy that is being used to manage the waste heat that we don't want. That is to say that every watt that you have in the data center as waste heat, there's an additional 0.4 watts that you pay just to manage that. So the long story made short is that there is a pressing need to do something about energy consumption in computing. If we look at the trends with microprocessors, this graph is perhaps a little bit busy. It has many things written on it. The curve that I want to draw to your attention to is that formed by the red points, which are the typical power consumed. So for people who are old like me, there was a very exciting time in history when electronics would change every year and you would buy a faster laptop or a faster desktop and you'd be amazed. Now those things have changed somewhat, and one of the remarkable things that has happened in the last 20 years is that the amount of power that is given out by a processor has flattened out at a level which is roughly 100 watts per centimeter squared. Why is it that value? It has to do with air cooling. How much heat can you pull out from a solid surface with just air cooling? It has everything to do with heat exchange, which we won't get into, but the practical limit works out to be about 100 watts per centimeter squared. So that is to say that in addition to the waste heat being a global energy problem, it is also doing something about how one can scale a microprocessor. And why do we have this energy consumption? So Gordon Moore, in his 1965 paper that led to Moore's law, had made many, many interesting remarks. One of them is, why do we have all this power? And he says, power is needed primarily to drive the various lines and capacitances. And if you look at a cross-section of a typical chip, you see semiconductor transistors at the bottom, they're really tiny. And then you see all the wiring above, they're very large. And charging these wires is essentially the main factor in energy consumption in a chip. To give you a sense of what the current state of the art is, the amount of energy consumed per logical state change, or if you want to be very formal about it, per logical state erasure, is 20 kilo electron volts. You may not know what a kilo electron volt is from daily life, but compared to the thermodynamic limit, that's about 20 millielectron volts. So in other words, it's about 1,000,000 times above what is a hard physical limit. So there is room for improvement. And where that room for improvement, how can we understand what we can do to get closer to that limit? It's by thinking about a little circuit model for transistor circuits. And I don't want to get into the details, except to say that the energy consumption, including both the static and dynamic energy consumption, if you know about this area, and if you don't, that's fine. The point is that it's proportional to CV squared, the energy to charge a capacitor. So the capacitance C has to do with the interconnect on your chip. That capacitance, you can't really do much about because it's given by geometric factors, but you can do something potentially about the voltage. And so if you then think about, well, how does a transistor switch on and off? And actually, I should have done this, and I apologize, I have not done that. Just to have a laser pointer. There we go. Now you can see where I'm pointing. So you have the log of current versus voltage, let's say, on a transistor. And you can ask, well, how small a voltage can I use to turn the transistor on and off? And that has everything to do with what's the rate with which the current gets turned off as you turn your electrical faucet, that is to say, your transistor off. And depending on what kind of transistor or switch you have, that will determine how fast this slope is. And right now, a conventional transistor, we are stuck with a limit of hundreds of millivolts that comes just from how the transistor works. So the question is, can we do something better? And that's the main point of the talk. So in thinking about this, let's take a moment to reflect on what people have done with computing in times past. And when I say times past, I mean really far in the past. So let's think a little bit about mechanical computing. So there are all kinds of fantastic mechanical apparatuses for the purpose of computing. You have things like the Astrolabe, which is essentially a fine instrument used to calculate things about the positions of planets and stars. There's this remarkable mechanism discovered from remains in ancient, that date back to ancient Greece, something called the Antikythera mechanism from the location where it was found. And essentially it was this remarkable box of gears that was again used for astronomical calculations. And we have more recent examples like Kelvin's analog tide predicting machine, which was essentially a way of summing up a whole bunch of sine waves of different amplitudes and phases, which was useful for the military in World War II to predict tides. So there is a precedent for using mechanical computing elements. There's also digital versions. So you have the Chuepu from Inca, the Swanpan from China, or the Roman abacus, and the slide rule. And if you think about more perhaps modern versions of mechanical computing, we have Pascal's calculator, which was a predecessor to mechanical machines for calculating bills, for example, at a grocery store. The famous Babbage calculating engine, and perhaps one of the more remarkable recent examples, Turing's electromechanical bomb, which was used to help decode messages being sent again during wartime. So there is precedence for using mechanical elements. Now, why then did we move from mechanical computers to electrical computer, like electronic computing? What's the reason for that? So if we reflect on it, it again has to do with energy. It takes energy to move physical objects. And you can think about, kinetic energy, and that tells you pretty much everything you need to know about how much energy it's going to take to actuate motion in some kind of mechanical structure. So it's then a bit counterintuitive. How could it possibly be the case that we're going to do something with mechanics to improve energy efficiency over that of electronics? So again, a blank slide for us to reflect very briefly. What is the underlying idea that maybe we should apply? So if kinetic energy is the key to understanding how much energy it takes for a mechanical computing element, then how are you going to minimize mechanical energy? Well, 1/2 mv squared, you have velocity there. That's not so obvious what you will do, but then you have mass. So perhaps we should do things that invoke very small masses. So we bring out the periodic table and we ask ourselves, what is the lightest element that we can use for mechanics? So hydrogen, that's a bit tough. Unless you are at the core of a planet, it's not solid, so it floats away. Same problem with helium. Lithium is great, but it's incredibly reactive. It oxidizes immediately upon contact to air. Oh, beryllium. Beryllium's great, except that it's toxic. So let's move on. There's boron. Boron is incredibly expensive because it is so rare on the Earth's surface. So then you go one over, and there we find carbon. Finally, an element that we might be able to use. So then we look at the carbon allotropes and what forms of carbon might be useful to us. So graphite is one interesting form of carbon. You have these atoms that are lined up all nicely in sheets. If you peel one of these sheets away, you have graphene. If these sheets were rolled up in different ways, and this is not how these other materials are synthesized, but you can think about it in your head as how you might synthesize them that way, you can have nanotubes and fullerenes. And of course, there's other allotropes like diamond. But from the perspective of trying to make mechanical elements, it seems like maybe graphene or carbon nanotubes might be a nice way to do it. And by using these materials, perhaps you can have very, very light and small elements that will take very little energy to actuate their motion. So let's think about graphene. Those of you that know me know that I'm very taken by graphene. We've done a lot of stuff with it. And why is it so interesting? Well, it's incredibly thin. If you ask how thin, it's about the thickness of an atom, and how you define that, I'm not going to get into, but let's say it's roughly 3 angstroms. What about the mass density? The mass density is 72 nanograms per centimeter squared. Maybe that doesn't mean much to you, but it is the lightest sheet of material that anyone can make. The Young's modulus, telling you something about how stiff it is 1 terapascal. This is at the upper limit. And so then you may wonder, wait a minute, if this material is so stiff, then that doesn't sound good for making any kind of switch out of it because it will take energy to deflect it. Hooke's law, F equals Kx, so K should be small. So thankfully, because the membrane or this graphene sheet is so thin, it takes very little force to deflect it because of its thinness. So in the end, it's the least stiff membrane that we know about. It's about a stiffness of 400 newtons per meter. Again, the numbers may not be immediately accessible, but I assure you it is the most flexible sheet of material that we can make because it comes about as a sheet of atoms. So one can synthesize these graphene sheets and then fool around with them. So here is an example of an experiment where we laid the sheet over some trenches. So on the right, you see an image taken with an atomic force microscope. And what that essentially is you have a tip that measures essentially the topography of the surface. So you can run the tip over the surface and measure where are there trenches, where are there not. And so that's, you see a sheet of graphene overlaid over some trenches in the image on the right. And moreover, you can take that tip and press into the membrane and figure out, well, how much force do you get for a certain amount of displacement? So you can essentially measure something like Hooke's law for the graphene sheet, but it's not a straight line here of force versus displacement. It's a little bit different. There's some interesting physics about that, but the point is that we can in fact understand this. And again, the numbers may not mean much, but the fact that it's hundreds of nanonewtons for tens of nanometers means that it is an incredibly flexible material. So take the nanos off and think about moving an object meters with tens of newtons. That is an incredibly flexible object. So you can do some cool things with this. You can make a capacitor, for example. So here's an example of that, where on the left you see false color electron microscope images of graphene sheets over trenches. On the bottom you see one graphene sheet over a trench. And one can measure the capacitance between the graphene and the substrate as a function of the voltage that you apply. So imagine you have a parallel plate capacitor. Then as you apply voltage, there's force between the two plates, and the flexible graphene sheet will move in. And so indeed, the capacitance increases as you apply voltage. And so that tells us that, well, it's not that difficult then to apply voltage and thus force to deflect the graphene. So that's kind of cool. And then how are we going to turn this into a useful device? So if you think about a transistor, a field effect transistor is essentially a capacitor. And how you turn it into a transistor instead of just a capacitor is to add some electrodes. And so that's the idea. And this is essentially the punchline of the talk, where our idea is to try to make a multi-terminal capacitor-like structure where you apply a voltage between a gate electrode, and when that voltage is applied between the gate electrode and the graphene, just like the capacitor example, we're going to deflect the membrane and then make a contact with another electrode so that there will be conduction. So that is shown schematically on the right. Now, the end goal is to achieve something that is shown on the left, where if we make a plot of the log of current versus the gate voltage, what we are essentially trying to do is make a miniature electromechanical switch such that you apply a little bit of voltage, the switch closes, you release that voltage, and the switch opens. And if we can get that voltage to be very, very small, then maybe we can make a more energy efficient switch than the transistor. So given that we know quite a bit about graphene now, we can make some numerical models, and those numerical models suggest that in principle, it should be possible to have an operating voltage of 100 millivolts for our switch. Current technology is running at 1 volt. So if you reduce the operating voltage from 1 volt on a chip to 100 millivolts, keeping all else equal, which is a tall order, but let's presume so, then that's going to reduce the CV squared energy dissipation by a factor of 100. So instead of 100 watts, you would have 1 watt of dissipation for the same performance. Now, there are many, many things that can go wrong and likely will go wrong as we try to implement this kind of switching device. But there is a clear path that suggests that we can do, in fact, better than conventional transistors. Now, does that mean that we will see the replacement of transistors with these kinds of switches? By no means is that clear. One thing that one should always keep in mind is that the semiconductor industry is the culmination of hundreds of billions of dollars over roughly a half century. And so many things have been optimized, so many problems have been figured out, that it is not so easy to introduce a new technology like this and just declare success. Even if it works, there may be economic reasons why it cannot be adopted. Things like manufacturing yield and so forth are incredibly important. But that's the main idea. And so I want to acknowledge collaborators at Université de Montréal and UQAM, students at McGill, Eli, Farzaneh, and Mohammed, and of course funding. And thank you very much for your attention. I'm very happy to answer questions.
Thank you very much for this very interesting talk. So if attendees want to ask a question, please do so in the chat window or by unmuting yourself.
Good morning.
Good morning.
Thank you, Professor Szkopek, for this talk. I wanted to ask about the relative size of the suspended switch compared to the size of a normal FET, since that's also.
Yes, that's very important, the density of the switches. So our current prototypes that we are working on in the laboratory are gigantic. They are of the scale of something like 30 microns by 10 microns. And so this has to do with the student having to be able to make a working device. And so it is not easy. So something that maybe we take for granted is that producing things at the scale, let's say a length scale below 100 nanometers, you can do it in a university research environment, but it is rather difficult, and not all processes can be implemented. So the idea is to start big and work our way to smaller and smaller sizes as we learn more about how to process the graphene and so forth. So in the end, in principle, it should be possible to make devices that have a similar footprint to a contemporary MOSFET, but that is a speculative and forward-looking remark that requires, let's say, proof.
Okay. Thank you. So do you think that by scaling down, the only challenge would be how to mass produce or to produce smaller chips, or will the physical properties of the suspended switch change as you try to scale down?
That is also a fantastic question. So there are some things that have, let's say, an absolute length scale. So if you take, let's say, two surfaces and you bring them closer and closer together, at some point, the two surfaces start to interact by what we call van der Waals force. And that van der Waals force becomes incredibly important for very small entities. So if we make a switch that is on the size of 10 by 30 microns, we don't have to worry so much about van der Waals. But as you make it smaller and smaller and approach, let's say, the sub 100 nanometer dimensions, then van der Waals forces are dominant. And there is relatively little that is known experimentally about how those forces scale with a variety of other external parameters, like how many electrons are in your graphene, for example, because the graphene is a conductor and you can, a semiconductor or a semi-metal, if you will. So if you change the electron density, that will change the van der Waals force, and these things are still not yet fully understood. So I would say that there's still some fundamental science to work out about how things would work at these very small scales. But there's no known showstopper. In principle, it's possible, but we may find a surprise that we aren't yet aware of.
Thank you.
Hi, I had a question. So given that we're deflecting the entire sheet rather than just charging a capacitor like in a MOSFET, wouldn't this use more energy to move the atoms rather than electrons?
So, okay, let's take a look at the cartoon above. So, or actually maybe the middle cartoons here. So you're saying when you apply a voltage, the fact that you're moving the atoms is going to somehow give you an energy consumption larger than that which you predict by, let's say, CV squared. And indeed, that does seem like a good argument. But if you think about the energy that is taken to deflect the sheet, so you have to overcome the mechanical energy, and that's the one that you are concerned about. But the fact that you are deflecting it means that your electrostatic force is balancing the spring constant of, or the let's say, restoring force that comes from the spring-like nature of the graphene. And so in fact, the mechanical energy is equal to the electrostatic energy, up to some prefactors depending on the shape and so on. So that is all still taken into account in this estimate that you can run at roughly 0.1 volts, and then you can still use the formula CV squared to get the energy, because it's the operation of the switch entails a balancing of mechanical force with electrostatic force.
Okay, and on a similar note, so like, would the frequency of the device also be limited given the inertia of the sheets?
That is also a fantastic question. I did not pay you to ask that question, right? We agree about that. So on the question of speed, this is also a very interesting reason why you should go to light materials. So one of the reasons I mentioned that the graphene has a low mass density of 72 nanograms per centimeter squared is the fact that then the amount of inertia that's involved or that total mass is small. So if you take Newton's law, F equals ma or F equals dp dt, and you ask, how long is it going to take to accelerate the sheet to make the contact? Then you arrive for typical kind of dimensions we have in mind, speeds that are in excess of nanosecond, or speeds that are in excess of gigahertz, or delay times that are shorter than a nanosecond. So it's on par with what you might want for a processor.
Yeah, thank you.
Thank you, Khaled. We have perhaps time for one last question. Okay. So I believe we will, thank you very much, Prof. Szkopek. It's really fascinating, the potential applications that may come with these graphene-based transistors, and many physics behind that still needs to be uncovered. So there we go. Yeah, sometimes it's difficult to change slide with Zoom, so this is my comment. Okay, So our next talk on in nanoelectronics and integrated systems is heterogeneous integration platforms with our keynote speaker, Prof. Boris Weisband. So let me introduce himself shortly. So Prof. Boris Weisband joined McGill University in 2019 as an assistant professor. From 2017 to 2019, he was a postdoctoral scholar at the University of California in Los Angeles. His research interests include the integration of heterogeneous systems, communication, power delivery, global interconnect, and thermal-aware design and floor planning, with application to the Internet of Things and biocompatible systems. He has worked for several high-technology firms as an intern. In 2015, he joined the power design team at Google Inc. in Mountain View, California. And in 2013, he interned with the optical and radio frequency research group at Cisco Systems Inc. In San Jose in California. And between 2008 and 2011, he held a hardware design position at Intel Corporation in Israel. Prof. Weisband received the Bachelor of Science degree in computer engineering from Technion, the Israel Institute of Technology in Haifa, Israel, in 2011, and a Master of Science and the Master of Science and PhD degrees in electrical engineering from the University of Rochester. So the floor is yours, Prof. Weisband.
Thank you very much, Kenz. Hopefully my introduction will be as Professor Szkopek's soon. You know, as full of achievements. So just started, hopefully. All right, so I'm going to share my presentation over here. All right, can you see this? I'm going to go ahead and assume that the answer is yes. Powered by the lectures. Okay, so we're gonna I'm going to introduce heterogeneous integration platforms. Actually, there's the previous talk was very, very interesting, and there's you'll see. I'll try to connect a few things as well, if I can, as we go. But first, so Ken's introduced. I'm gonna go over the slide anyway because I was born in Russia. I grew up in Israel. I lived in the past decade almost in the U.S. and moved to Canada about a year ago. Started working at McGill. I am married plus. Married is my amazing wife. The plus is my two amazing daughters. Education and work, Ken's mentioned already, so I'm going to go over that. I teach digital logic. Previous semester, this semester, not next semester. I also teach ECSESS 6A2, which is topic computers and circuits. It's also going to be related to heterogeneous integration, so if you want to learn yet more about that, you're welcome to, and you're a graduate student, you're welcome to join that. My team includes currently 2 PhD students, and we are growing. All right. Okay, so I'm going to give you a very short history of integration and how things came to be about. In 1947, a guy named Shockley with 2 other guys were Union Britain. They invented the point contact transistor, just the one single transistor. It was a big deal. We then followed, and I am skipping a whole bunch of years and inventions in the middle, but just to hit the ones that I care about right now. Jack Kilby came up with the first integrated circuit. Okay, this thing was very simple. It was a germanium slab generating a sine wave. That's it. That's all it did. Not so much successful. Actually, Noyce was more successful, coming up with a silicon-based circuit just a few months later. But that was highly adopted. As Professor Szkopek said, a lot of investment into silicon and CMOS in the last probably 5-6 decades. Effectively, from that point on, and almost to date, we are in a constant, non-ending race for functionality, improved functionality or increased functionality, higher speed, lower power, which was the motivation of the previous talk and super important, and area. And the nature of us as people is that we're greedy. We want everything, and we don't want to pay for it. Pay in, for example, power and area. That's also a form of payment, but also in dollars. So this race had all sorts of limitations. It had all sorts of inventions that overcame challenges, multiprocessors, and other important inventions. But now we've reached, in the past about decade or so, we reached a new point where we want what we call heterogeneous systems integration. The next slide, if you're going to ask me what it means, the next slide is hopefully going to answer that. We're going to focus on this. The idea is we want more. We want more functionality that is disparate. And we want it as close as possible to each other. And we want it to operate at highest speed, lowest power, take the lowest area, and so on. And you know, the simplest example is everybody's cell phones that you have in your pocket, smartphones. They do everything today. You know, my wife just told me yesterday, I don't need a camera. I can just use a new phone. You know, it can replace my camera. And that's just one example, but in fact, it can do so much more. So what is heterogeneous integration really? It's really the next step after what was called VLSI, very large scale integration. This is the race that I discussed earlier. It's the next step. We take a system level view on our circuits or systems, right? And we look at disparate materials, disparate technologies, functionalities. We want to take all of that and bring it as close together as possible in order to achieve the best performance. We want it to look as if it was fabricated in a single process. Say I have this green big die. Die, if you don't know what die means, it's basically, it's like a chip. You heard of the word chip. So die is an unpackaged chip, basically bare. Okay, and I can have it fabricated in a certain technology, 40 nanometer, for example, which is, you know, the basically relates to the size of transistors that we have. I could have a smaller die at 28. I can have multiple dies and other technologies that were fabricated in different facilities, different fabs. That's how we call that. We could have completely different technologies than transistor-based technologies, like MEMS relates to what we heard a little bit, what we heard before. We can have discrete components. These are the, you know, if you open your computer and you look at one of the boards, you will see these big capacitors, for example. So all of that. And we want to place all of that on a single platform, some platform, so it looks like as if it was fabricated in a single monolithic process, as if it was. It wasn't, right? Because each has its unique technologies, unique processes, unique approaches, unique tools, and so on and so forth. But we want it to look as if it was. Why? Because when it's so close, when it's so tight, one of the greatest advantages, and I probably can just take Professor Szkopek's slide, his first slide on energy, is we're going to save a lot of energy. And the other performance aspects as well, as I mentioned. What are the target markets and applications of this work? Well, you can probably find yourself in one of these columns with almost any application. So, and that's true. The applications market is very, very wide. It goes to Internet of Things devices, so potentially small devices, billions of very small devices that are highly heterogeneous. Every IoT device that we want to place somewhere, it will require some control. It will require some memory. It will require sensing, actuation maybe. It will require communication. So it's a very highly heterogeneous device. How do we make it very, very small, a small footprint, very small energy footprint as well? For example, energy harvesting could go in there. Smart mobile, I talked about mobile devices. It's and I think it's been taught a lot. So not much to add here. Highly heterogeneous device. It can do a lot, perform a lot of functions. Data centers. Data centers is a big deal. Again, as was already mentioned, they consume a lot of power. How about if we could take a whole data center, which is, you know, maybe the size of a hangar, right? You know, with a whole bunch of racks. These racks have a whole bunch of servers, right? If we could take this whole hangar and place it in a small room, the size of a small room, how about that? That'd be great, right? We'd be saving much energy in operating this. Cooling would be difficult, but much better than what we have right now. 0.4 watts for every watt. That's a lot of overhead to cool. Autonomous vehicles, all about sensing, real-time compute, very fast, very accurate, very important. Wearables and health, that's a big deal. Heterogeneous integration targets this area as well in biocompatible platforms, or the systems that can go within the human body or on the human body, sensors and so on. Aerospace and defense as well. There's a whole bunch of projects that I could probably describe that require real-time compute, very large amount of data to be computed fast, and then everything from platforms that can cover, flexible platforms that can cover, say, a wing of a plane, right, for all sorts of LiDAR applications. And there's a lot of words that, if I could go explaining every single one of them, I'm not going to finish ever. So I'm going to leave you with just these sort of 6 pillars in terms of markets and applications. These are of interest. We're targeting them. In fact, there's a whole in the reference here, there's a whole roadmap for heterogeneous integration that describes not only the targeted applications, but also zooms into the various platforms and so on. So that's a good source for information as well. So what is a heterogeneous integration platform? Right, so I said, okay, we want those functionalities close together. We want disparate materials, processes, technologies. But what is this platform that I talked about? A platform is some substrate, maybe, right, or some structure that will hold all those functions together, right? That will include them. So here's an example, right? This is in the middle, this cartoon, right? This is a rigid substrate of some form, maybe silicon, maybe something else. And it holds a whole variety of circuits and systems. Some of them are three-dimensional, like this one on the left. Some of them are maybe large converters, inductors. We can also have, you see, systems on the back of this thing, right? So when I say we can have, this is a vision, right? We don't have this today. No, not at all. Not at the level of integration that we want, but that's where we want to go. And we could have processes, we could have memory, we could have RF devices, radio frequency devices, we could have fine pitch integration approaches, we could have antennas, and so on and so forth. Every single component here, it has its own specifications, has its own processes, has its own technology that is optimized for that component, for that function. The question is, this is the big question, how do we bring everything together such that it coexists within a single platform and optimizes all the performance parameters that we care about? Some additional platforms, just to kind of tease you. Here's a three-dimensional platform where every single layer is fabricated separately to accommodate a certain function again, right? It could be a separate technology, it could be a separate process, it could be compatible with, for example, electromagnetic and solar energy harvesting, or it could have some what's called in the defense industry trusted layers, right? We can play all sorts of games here, but the idea is three-dimensional layers that are stacked one on top of the other to perform a multifunctional operation as a system. Here's on top, here's a flexible biocompatible platform. You see it is actually wrapped around the pen. This thing is not printed electronics that is somewhat bendable. This thing is fully flexible. You can take it in your hand, do like this, throw it out, and it has dies in it and interconnects in it. It actually performs a function. Those dies could be anything we want. We could have wafer scale systems. This goes to the data centers or high performance compute that I described earlier. We could have a whole wafer that will accommodate a whole rack or multiple racks of servers. So a lot of CPUs packed in together within a single wafer. This wafer is maybe 300 millimeters in diameter, but it includes the compute power of a much larger system. So what are the research topics that are of interest? describe the platforms, I describe what we want to do and why. But what do we actually do? What we do is we design methodologies for heterogeneous integration platforms. What does that mean, methodologies? There's a lot of words on this slide, on purpose, maybe to so you see that there's really a lot to do. Okay, we're not going to run out of work soon. The question is, say we have a certain platform, say we target a certain application. How do we place our components? What is the platform that we're going to use first? Is three-dimensional integrated circuits a compatible platform for our application? Maybe we want something that is flexible. Maybe we want something that's biocompatible. Maybe we want something that fits, an ultra-large system, and so on. How do we place our components? How do we interconnect our components? Wiring is very important, both when we target local communication, very close, or very far. That's a whole different problem. How do we deliver power to our components, right? So think about it. If I have a three-dimensional system, okay, and I want to be delivering power to the lower level layer and to the top layer, and I want both of these to be at a certain quality. And also, when we talk about delivering power, we talk about the thermal aspects of it, three-dimensional circuits. It's a special challenge because heat becomes trapped within the structure. So we have to solve that as well. How do we distribute a clock? Just today we talked in my class in digital logic about synchronized systems, right? That we have to clock everything. Well, do we really have to clock everything? The answer is not always. Sometimes we clock parts of our systems. Maybe some parts are asynchronous altogether. But if we want to distribute a clock across, say, a very large system, how do we do that? Wirelessly, wired. There's a whole bunch of questions there. Testing is a big deal. How do we verify that our platform, that our components, and the total system, the complete system, actually functions, actually works, right? So there's all sorts of topics of built-in self-test. There's built-in self-test and repair, where we can sometimes reroute if something doesn't work in algorithm or actually in circuitry. So what we do is we do modeling, we do algorithms, we do simulation, and we do prototyping. Each of these words actually includes a lot. I can probably be talking for a whole lecture just about modeling, right? What does that actually mean? But you can think about anything from modeling a wire with an R, an L, and a C, depends on what kind of wire. May or may not have some of these components, or at least one of these components. We develop algorithms. Those algorithms will go into our automatic tools that will help us perform the tasks that I list here, right? Floor planning, for example, routing, for example. We want to optimize all of these approaches for these platforms in order to get the best performance results. Simulations, prototyping is effectively building, designing and fabricating with our partners in industry and academia, smaller prototypes of our systems and testing them. We look into novel materials, so there's a lot on carbon-based materials. We have, for example, we collaborate with Nanyang Technological University on CNTs. So one of the questions I would ask Professor Szkopek would be, those devices are amazing. I truly think it's amazing. Okay, and I think the future is there. Yes, it'll take a lot of billions of dollars, but maybe we'll get there. But then what about interconnect? How do we connect that to a copper metal interconnect, right? So we've looked into that problem a little bit. Various integration platforms, I mentioned that. And collaboration is really key here. The projects are very interdisciplinary. Sometimes it's in the medical field, sometimes it's with mechanical engineering, with material science, and so on and so forth. So we get to work with all those people. Currently, we have a couple of projects on power delivery and hardware security. And actually, what I'm going to do in the next couple of slides is I'll give you an example of a research that we're doing right now, and one that is future research in the next slide. So here's an example of something that we're working on today. It's an hardware obfuscation, hardware security project, where we're relying on a patent that is cited here that came out. The idea here is We want to make sure that what we fabricate stays secure, as in whoever fabricates our design doesn't know what the design does, right? So they fabricate it as a black box that they don't know what it does. If they have the entire design, they will be able to do what's called reverse engineering, right? And they'll find out what the function does. This is highly of interest in the defense industry, and in fact, this project is supported by the defense industry. The idea here is we want to separate what's called front end of line, which is basically the transistors, from the back end of line, which is basically the interconnect. And again, I could use Professor Szkopek's figure, which is very good. Maybe I'll use it next time, where you can see the transistors on the bottom, they're tiny, and the metals on top, which are huge. So then we want to separate those two, fabricate them in separate, what we call fabs, I already mentioned. So basically facilities, fabrication facilities. And then we'll integrate the two parts afterwards, right? So effectively what we get is each facility has only part of the design. They don't have the entire thing, so they can't really do anything with it. Now the question is, where do we split? Can we split really at transistor metals? Not really. Can we split at, you know, a certain amount of metals? So say transistors and 2 layers, is that enough? In terms of what? Enough in terms of performance on the one hand, obfuscation on the other hand, right? If I have 20 layers of metals, so maybe that's okay. But if I only have 3 or 4, splitting it 2 or 3, maybe that's not enough, because the last piece could be inferred, maybe, okay? So these obfuscation levels is what is of interest. In fact, we're designing now a prototype where we're gonna look at various structures on a unique integration platform that allows this whole operation of fabricating separately and then integrating together. It's called the silicon interconnect fabric. It's a very fine pitch integration. Fine pitch means very small vertical interconnections. It looks as if almost it's a single process. This is, remember, I started with this. This is what we want. We want to take things, fabricate them, and then attach them together as if they were fabricated like so. So this is one example project. I don't know how I'm doing on time. I think I have a few more minutes. Hopefully this inspires you to learn more, and generally speaking, for research and academia. You're welcome to contact me if you have any more questions. Website is over here. Email is available, and so on. Thank you very much.
Thank you very much, Prof. Baseman. It was very interesting, really, a promising project in brain simulation, and thank you for introducing the critical issues and platform security and integrity, and as well the underpinnings of the next big thing in computing devices, so the integration of heterogeneous systems. So we have 5 minutes for the questions, so please unmute yourself. I believe Amar, the co-organizer, has some questions for Prof. Baseman, so you have the ground.
Thank you, Kens. Thank you, Professor Weidman, for this interesting talk. I was wondering if you could clear for me, should heterogeneous integration platforms, especially for mobile applications, be thought of as an extension of system on chips, or are there fundamental differences in how to think about those two things?
Well, yes, definitely. So what is a system on chip? As I mentioned, we are all greedy as people. A system on chip is our attempt at integrating more and more functionalities into a single system on a single chip. But the limitation, well, there's a whole bunch of limitations there, but the problem there, it is not heterogeneous. So if I want a system on chip that, for example, includes a circuit that's called SerDes. SerDes is serializer, deserializer. Okay, if I want to be communicating with other chips, I need that circuit because there's just not enough room for parallel wires. Okay, so say I want to design a new system on chip at a better process. I'm going from, I don't know, 22 nanometers to 14 nanometer process. What I have to do is I have to redesign the entire system on chip at 14 nanometer. But hey, you know, my SerDes works just as good at 45 nanometers, no problem. Why do that? Think of all the what's called recurring engineering hours, right, or effort that will be put into that. But instead of doing that, I can just split my huge system on chip. The systems on chip of today are hundreds of millimeters square in area, hundreds, 600, 700 millimeters in square in area. These are huge systems that have a ton of issues. If I split this into smaller functions, I optimize my yield, I optimize my cost, I optimize my performance, and then I put it onto something, some platform, magically, right? That will allow it to look as if it's a system on chip. So yeah, I guess it was a very long answer to a very simple question, but
No,
the answer is yes.
Thank you.
Thank you. I think